Microsoft, which means that essentially I don't really understand deep learning very well. But when I learned about it, I worked with amazing people, most amazing of all, Cesc Juarez, who's fantastic. Hank actually understands most of this stuff really well as well. So this is great, and then they help me understand things, and then I thought, wow, it's interesting because they keep using words that I don't know what they mean, and we do the same as software developers, right? We use fancy words because we think it puts us on a pedestal. And so I thought, well, I should do a presentation where I'm kind of translating those words and also some of the concepts. So we are going to do some math. You can leave if you are scared. No? It's easy math, okay? And I'm going to really go through the step and explain to you what those things work. But essentially, the first thing to realize is that AI in our brain, we have a lot of concepts, which many of those concepts come from movies, right? So Hank and I were talking about that yesterday. You recognize that movie? If you're my age, you recognize that movie clearly. This is War Game, okay? So War Game was, as a kid, well, I was probably just a little bit more than a kid, like a teenager, I guess. It's like the first time I went to a movie and I saw, wow, this computer can think. That's amazing, right? But at the same time, he also wanted to destroy everyone because it misunderstood that it was not playing a game. So that's bad. And then if you go even further in time, you recognize that dude? Okay, that's HAL from 2001 Space Odyssey. HAL, you know why it's called HAL? Because the letters IBM, and then you take one letter before, it's HAL, HAL, okay? So this one was developed in the mind of Arthur C. Clarke and then later Stanley Kubrick in a time where computers were unable to do any of that, okay? People had not even gone to the moon when Arthur C. Clarke wrote 2001 Space Odyssey with a sentient computer. And of course, that computer wanted to kill the crew because it has some kind of moral conflict. So that's bad, right? Now, this one is way easier. It just wants to kill everyone. He doesn't have any moral conflict at all. It's just like kill and destroy, okay? So basically, when we think about AI, I guess my point here is that we have a lot of, wrong ideas. And it's not just us who have wrong ideas. Marketing has wrong ideas as well. This is an actual rice cooker that I actually took a picture of myself in my actual kitchen. And you see, it's it's actually using artificial intelligence to cook rice. Now, I'm going to assume two things here. First thing, you don't need artificial intelligence to cook rice. Okay, generations of Asian people have been doing that for years and years and years and centuries, and they don't need artificial intelligence. Second of all, I'm going to go on a limb and pretend there is no artificial intelligence in that device. It's probably just a series of ifs then else, maximum, right? Like checking the temperature, the humidity, is the rice cooked? Yes, ring a bell. You know, that's pretty much what it does. So anyway, we have a lot of preconceptions about AI. So let's go a little bit into that and understand a little bit how those things work. But first of all, I want to manage expectations. We have 60 minutes. Okay, I have 52 slides. So even though it's a gentle introduction, I'm going to go a little bit fast, right? And also, even more important, I don't really know what I'm talking about because it's not my profession. I'm a developer. But I'm going to assume that many of you are developers as well, so at least we speak a similar language, all right? This is the NDC, the Norwegian Developer Conference, which is in Porto, and so maybe the D is more correct than the Norwegian part, but nonetheless, hopefully we speak the same language, so that should work out. So let's understand some concepts. Deep learning, machine learning. Let's start with intelligence. What is intelligence? Well, intelligence is a capacity that something or someone, let's put it this way, has to learn from experience, but most importantly, to apply these learnings later in life to gain some benefit, all right? So you're going to say, oh, if I shower with warm water, it's better than cold water. So next time I'm also going to shower with warm water. Just an idea from this morning in my shower. I don't know. It's not just for humans, right? Animals do that all the time. Okay, you have some very intelligent animals who actually learn from an experience and then they apply that later. And in some cases, they even pass that to further generations, which is really cool to observe. So that's intelligence. And of course, a machine can be intelligent, can have some intelligence at least, and that's what we call artificial intelligence. So that's exactly the same concept, but applied to a machine. And then you have machine learning. Machine learning is a subset of artificial intelligence, if you want, where you teach a machine to do something with different ways. And one of the ways of teaching a machine is called deep learning. So again, this is a subset of machine learning. And in deep learning, what you're going to do, you're going to give some sets of data to a machine and let it learn in different ways. But very often you try to let the machine learn in a fairly independent way. All right? So that's the definition of deep learning, if you want. Now in this talk, we are going to talk more about supervised learning. So we could argue if it's really deep learning or not, but essentially it's machine learning, let's say. Cool. So let's understand a little bit some concepts. First of all, many of us are developers, right? So I guess maybe there are some data people in here, but nonetheless, when we program, when we code, what we do is that we take an algorithm, okay, very often from Stack Overflow, copy paste, or we just, check in a book, how do we do things? How do we sort, a big table in the most efficient way? And then we translate that into code. And then we take some data, and we run that through the code, and we get some answers. Okay, that's a typical way that we create programs. In machine learning, things are reversed in the sense that we are going to feed answers into the system. So this is where we teach the machine. We say, all right, this is a pizza. This is a picture of a pizza. This is a picture of a hot dog. Those are answers. And then we are going to take some data, some training data, all right? And then we are going to get that through a framework. TensorFlow is a framework. PyTorch is a framework. There are other frameworks like that to train what we call actually an algorithm, but in machine learning, they call that a model. And this model is then going to be used inside some additional code with the actual production data, the data that you want to test for real, and you're going to get not answers, but you're going to get some predictions. Predictions are different from answers in the sense that answer is, yes, no is an answer, but in machine learning, we don't really get clear answers. We get, well, there is 85% probability that what I'm seeing here is actually a slice of pizza and not a hot dog. All right, so those are predictions. And of course, a prediction can be good or bad. And then after that, if you train your model better, maybe you can get better predictions, or maybe not. It depends a little bit. Okay, so it's less precise if you want. Now, one thing that I want to mention also, I told you that, we have some sentient computers in movies for a very, very long time. Actually, if you go back in time, the neuron model, we are going to see what is a neuron a little bit later, was developed in a theoretical manner in 1943. That's really long time ago, all right? And in 1955, there was the first AI conference, which is 14 years before men went to the moon with very primitive computers by today's standard, okay? So those things have been in the mind of people for a long time. But it's only recently that we got an explosion of actual implementations of those things. So why is that? Well, there are a few reasons. First reason, data. You need tremendous amounts of data to train a computer to create a model, to train a model. And until now, it was not economically viable, because this data, you have to collect it. So you need sensors, you need all kinds of devices to collect the data. Then you need to store it. And now we finally have those capabilities, all right? So on Azure, for example, we store, I don't know what is bigger than petabyte. It's, I don't know. So I remember when I started working in Azure, I was seeing terabyte everywhere. And I was like, oh, that's big. And then suddenly I started seeing petabytes everywhere. And I was like, oh, that's even bigger. And now, in 2 years, we are going to see something even bigger. And this will just become natural language because it's growing at tremendous rates, right? That's the first thing, data, being able to collect data, store data, and then process data. Now, in order to process data and to train machine learning models, you need GPUs. Now, GPUs are very expensive these days and very rare to find because there are some Bitcoin people who think that, oh, this is cool, we can, earn some money with that. That's another problem altogether. But basically, GPUs are really useful because they can process data in parallel, and we'll see in the maths why this is important when we talk about linear algebra, sorry. And so until recently, we didn't have GPUs powerful enough, so training those models would take a very long time. But now we have very powerful GPUs. So when I say now, I'm talking like 10 years back and until now, right? And then now we can really process in an efficient manner. And finally, advances in software. All right, Python, for example, has tons of libraries where you can do a lot of things in a very fast and direct manner. You have to write less code because the software is more efficient, and so this works well. So that's why now we see really an explosion in AI and deep learning and machine learning. So now let's talk about those concepts: neural network, and this is like the building piece of those models, really, those AI models. So first of all, let's just take a step back and imagine that we have a system with a number of inputs. Okay, I have x1, x2, I have xn. I have a variable number of inputs. And for some reason, we decide that we want to multiply the first input by something, w1, and then the second input, x2, by w2, and the nth input, xn, by wn. And we do a product of that. And then we decide we want to sum those products and get an output, which is y. So if you want to express that in a mathematical manner, if you want, we are going to say y equals the sum. This is sigma. It's a Greek letter, all right? It means the sum of. And then for developers, we understand that very well because we go from 1 to n. All right, we would probably go from 0 to n minus 1, but whatever, it's the same, right? We go from 1 to n, and then we take the first input times the first w, and then we add the second input times the second w, and then we do that n times. Okay, it's a loop, it's a for loop, essentially. So that's cool. But then another thing, we decide we want to refine our system a little bit. And by the way, those w's, we talk about weight in machine learning. And because an input can be anything and the w can be anything, we have an output which can be literally anything from 0 to infinity or to minus infinite to plus infinity. It's not very convenient. So probably we want to normalize this. For example, between 0 and 1, that would be cool because 0 to 100% I understand better than minus infinite to plus infinite, right? So we use for that a nonlinear function, which, by the way, in machine learning is called an activation function. And this activation function is going to take the result of this sum of products and then transform that in something that we understand better. Okay? And so if I add this to my mass that I had before, now we have the sum of products that we had before, but now we are going to pass that through a nonlinear function. And we'll talk about those activation functions a little bit later. Now, finally, when I look at my system, I say, well, that's really cool, it works well, but it would be cool if on each separate piece here, I had a knob that I can turn to adjust things a little bit, okay? And so this is here, we are going to take the value 1 and multiply it by a value b. And this b is called a bias. Nothing to do with the bias when we talk about ethical AI that I'm going to talk about a little bit later. This is just a mathematical term or a machine learning term. And this here, it basically allows me for each separate neuron, because this is a neuron, it's going to allow me to adjust things. Now note that at no time I told you what those W's and those B's are and how they are calculated or computed or found by the computer. We'll talk about that later, okay? But this is a model of a neuron. And because machine learning people love to use words that nobody else understands, for some reason somebody said, hey, we should call that a perceptron because this is so much cooler than a neuron, right? This is the same. So now again, if you go into our math and we add the bias, this is how it looks like. Now this is a mathematical formula of a neuron. Now the problem with that is that when you do a for loop it's a serial exercise, and it takes a long time. You're going to start with x1 times w1, and then you're going to add x2 times w2, and then you're going to go, and you do that in a serial manner. This is going to take a very long time. And this is where linear algebra comes in the game. Now, don't be afraid, okay? This is actually pretty cool. It's even cooler because I learned those things 30 years ago, and I never used it until today. So finally, my math teacher is, I told you you're going to use it someday, and this day is today. So this is so cool. So let's talk about vectors, right? Vectors are really cool. They have dimensions. This is a vector with 2 dimensions, x and y. And if I want to draw that on a piece of paper, 2 dimension is very easy because we live in a 3-dimension world. So 2 dimension is 1 dimension less. So this is the representation of this vector. It has an angle and it has a length. All right. And of course, you can have vectors with 2 dimensions. Now we have vectors with 3 dimensions. All right. 3 dimension, I get it because we live in a 3-dimension world. Okay. I can come to you. That's an axis. I can go up. I can go left and right. So I have 3 axes. Now, of course, if you add a 4th dimension, it gets really complicated. And if you add n dimensions, then suddenly our head explodes. But for a computer, n dimension or 2 dimension is exactly the same. It's just going to take a little bit longer to process if you have n dimensions. But it's exactly the same. Computers don't live in a 3-dimension world. They just take the data, we feed them, and they process it. That's what they do. So one mathematical operation that we learned in school is called the dot product. It's a product of vectors, and it is expressed like that. It's essentially the first line, the product of the first line, plus the product of the second line. Okay? And this is cool because a computer can do that operation very fast, and especially a GPU. So we go back to the GPUs, because what do GPU do? They are graphical processing units. They take an array of things, of pixels, and then they multiply that by another array of pixels, by another array of numbers, to create something. And that can be maybe a filter, for example. Okay? In computer science, we talk about shaders for those things. Essentially, you take an array of pixels, which are the pixels on your screen, and then you multiply that by something to create an effect. Like if I multiply everything by 0, I have a black screen. That's exactly what the GPU is doing to create a black screen. Okay, if I multiply everything by 2055, I get a white screen, okay? Because the maximum for a pixel is 255. So GPUs have been designed to process those pixels as efficiently as possible. And now we use this capability to process linear algebra in a very fast manner. So instead of doing, first of all, I'm going to do 3 times 4, and then I'm going to add 2 times 5, which is what my brain is doing, my linear brain is doing. The GPU is going to do that in 1 pass, okay? Much faster. So if we have 2 inputs, this is what it is. If we have n inputs, well, essentially that's what it is. This is exactly what we had in our neuron. It's a sum of 1 to n of products, okay? Which means that we can say a neuron looks like that, but except that this part is going to go way faster for the computer. And this is why they are very efficient at doing these kind of things. All right, so let's simplify the notation a little bit. So here I have a number of W's and a number of B's. I can simplify the notation by implying a few things. I'm going to say, all right, the W's are here, the bias is here, the nonlinear function is here, but I just don't draw them for the sake of simplicity. Because drawing those things in PowerPoint takes a long time, so I remove them. And then after that, let's say, data scientists very often, they try things out. And they say, well, okay, so now I have 1 output, this is cool, but what if I want more than 1 output? So I'm going to add another system, another path, if you want, and then I have 2 outputs, which means that I have double the W's and double the B's. And at this point, I didn't tell you yet how we are going to find those W's and those B's. Then they say, oh, that works actually pretty well. But what if we do that? We add even more W's and B's. And the more W's and B's you add, the more paths you add, you notice that your system is more precise. This is cool. Now, of course, there is a limit at some point. The limit typically is when things take too much time to process and they don't improve the results significantly. So there is a point in time where we stop. Nonetheless, this is cool. We have a hidden layer now, all right? I can measure the input and measure the output. I cannot measure what is in the middle. That's my hidden layer. And what if I added even more layers? And then we notice that, okay, the result is getting better and better, but at some point it's not worth adding layers because it's going to take way more time to process, to calculate those W's and those B's. But nonetheless, this is basically a deep neural network. You talk about deep neural network when you have a lot of neurons and a lot of layers, okay? So let's talk a little bit about the activation function. This non-linear function, which is transforming pretty much anything into something that we can compare, 0 to 1 or -1 to 1, for example, depending on what we need. There are a few of those functions, and again, things in data science progress very much by trial and error. So they try things, they say, oh, that works great, so let's do that more, and then they try something else, and oh, that works even better, so let's try that even better. So for example, an activation function could be a sigmoid function. This is a mathematical formula, E being 2.71. It's a constant which is important for the world, Euler constant. Nonetheless, if you plot that into Excel, which is literally what I did, this is what you get. Now this one is cool because you see for very negative numbers it's 0. For very positive number it's 1. So essentially I'm saying, all right, I'm going to ignore everything which is at the edge. I'm ignoring that. And I only concentrate on the stuff which is in the middle where it's really significant. There is a significant change. And we go, and the slope can be more or less steep depending on the numbers that you put in the sigmoid. All right? So you're going to adjust your system like that and say, all right, now I want to go from 0 to 1 with a slope which is more or less steep. And then there is another activation function which is used a lot, which is called rectified linear unit, or ReLU. And ReLU looks like that. It's a ramp. So essentially what the ReLU does, it says everything which is negative, I don't care. And everything which is positive, I want to take it as is. And typically in a system like that, you're going to have a lot of those activation functions, and then they are going to take, at some point they are going to take a ReLUs, and the next time they're going to take a sigmoid, etc. And then they are going to try things out until something works really well, and that's a model if you want. Okay? So a lot of concepts. We still don't know how to calculate those W's and those B's, so let's make an example, okay? So the problem that we have here is we have this 9 square, and we want to find out in the most efficient way possible if the top row is darker than the bottom row. Now in that particular case, I would say it's pretty much a tie. I think the top row is a little bit darker than the bottom row. My eyes tell me so. Of course, if I want to do that in an efficient manner, I need to find a way to automate that. So let's do that. So first of all, let's give numbers to those squares. Now I'm going to say that very dark is 255, and very light is 0. And I know this is the contrary of what the computer does. Okay, for a computer, 255 is white and 0 is black. But it's easy to reverse, and it makes my life easier. And I don't know for you, but I like my life to be easier, so I'm just going to reverse. So here I have medium gray. Now I have something darker. Now I have something lighter, so the number is smaller. Something more or less the same. Something more or less the same as above. You see there is only one difference, right? Now something very dark, almost black, almost 255. And then etc., etc. At the bottom I have something almost white, almost 0, okay? So let's imagine that I have a lot of those numbers, all right? This is a lot of data, and I want to find an efficient way to calculate that the fastest I can. So let's apply what we learned. We have 9 inputs, 9 squares, okay? Then I'm going to run those inputs through some W's, so some weights. And then I'm going to do the sum of those products. And then to make things easier to understand, I'm going to say, all right, I'm going to create an activation function which returns either 1 if the top row is darker, or -1 if the bottom row is darker. Okay? So I'm going to concentrate only on those 2 values. That's all my activation function delivers. Now, how do I find the values of those W's? Well, I can think about it because I'm a human. That's my advantage over a computer. And I can try to think what makes sense. So first of all, let's feed some data into those systems. So this is, a square. Obviously, the top row is darker than the bottom row. My eyes tell me so, but if I was vision impaired, I wouldn't know. So let's see how we can calculate that. So I'm going to put those inputs there. And then, I told you I worry about the top row. I worry about the bottom row. I don't care about the medium row at all. So the middle row, I can say, well, I'm just going to ignore that. It doesn't influence my system at all in that particular case. And then after that, I can say, well, okay, if the top row is darker, it means that the sum of those values is going to be larger than the one at the bottom because dark is high in value. So the higher you go, the darker you are. You could average it, but you see the cool thing is that you don't even need to average. If the sum is higher, it's going to be darker. So I don't even need to average those values. So I'm going to say, all right, the top row I'm going to multiply by 1. And then since I want to compare, it would be cool if I had a negative value at the bottom row so that I can do the sum. And if the sum is positive, the top is darker. If the sum is negative, the bottom is darker. All right? So I'm going to multiply the bottom row by -1. Then when I do the sum, I get 495 on the top. I get 259, but I change the sign because I want to add things at the bottom. The bottom is clearly lower in absolute values than the top, which means that the result is going to be positive. So if I run that through my activation function, I'm going to get +1. You see the thing? Now, here, I was able to find the values of those W's by reasoning. And a computer cannot do that. But computers have an advantage over us. They can do things very fast. So what they are going to do, they are going to try, then they are going to check the result, then they are going to try again and check the result, and if it's better, they are going to take rather that path. And this is what they call error reduction, right? But first of all, let's understand a little bit a few more terms, a little bit more vocabulary. Very often we talk about supervised learning and versus unsupervised learning. So supervised learning means you're going to train your computer with some examples. You're going to say, all right, I'm going to give you 1,000 pictures, and more or less half of those are going to be pizzas, half of those are going to be hot dogs, all right? And then you're going to learn from that, and then I'm going to try with some new data, and we are going to see if you get it right. Okay? So that's supervised learning. This is great for image classification. When you want to find out, you have a set of labels, pizza, hot dog, bagel, etc. And then you have a set of image and you want to classify them. That's called image classification. Now you can also do unsupervised learning, where you basically give an algorithm and you give some data to a computer and you let the computer sort things out by themselves. For example, by checking the pixels and clustering them. Like for example, they will cluster darker pixels. So they will notice, all right, there are some eyebrows, there is a nose, there is a line here, might be a mouse. I think the probability that it's a face is pretty high. Okay, so that's good for things like image recognition, which is different from image classification. Okay, you see the difference. Image recognition is more of an unsupervised task. It's more of an autonomous task that the computer is doing. All right. And then you have also something which is called reinforcement learning. Now this is a little bit how you train, for example, an animal. When you want to train them, all right, you teach them a trick, and if they do the trick well, you give them a treat. All right. I'm not sure what a treat is for a computer, but you have ways to do that apparently. So again, here I'm a little bit at the limit of my knowledge, right? So those things are, commonly used. They are words that we use a lot, that we hear a lot when we learn about those things. And moving forward, we are going to talk more about supervised learning. The example I have is more of a supervised learning thing, of an image classification thing. All right. A little bit more math. Okay, stay with me. Stay with me. Remember how you find the slope of a function at a given point? Well, it's called a derivative function. So let's imagine that you have y equals square of x. Okay, this is the curve here. Again, my Excel skills are absolutely fantastic. As you can see, I can do graph. That's great. Now, let's imagine that I want to run a line through 2 points on this curve. And I want to find the slope of this line. Well, we know from math that we learned long time ago that the slope is equal to the vertical difference divided by the horizontal difference. This is the formula of the slope, right? Now I know about the slope in those 2 points, but if I want to know about the slope in one given point of this function, what I can do is make x smaller and smaller and smaller until it's 0. Like this, I will have only 1 point when it's 0, okay? I know it blows the mind a little bit to think about that, but basically in math, we say we are going to take x, delta x, and we are going to let it tend to 0, all right? And it's going to get smaller and smaller. Now I still have 2 points because I zoomed in a lot, okay? But imagine that if delta x is 0, I'm going to have really just 1 point. And the slope at this point is going to be 4, y equals square of x. We know because we learned that by heart in school, and maybe it's a hard realization that, oh my God, I learned that at some point in my life and I never used it ever before. Well, we know that the derivative of square of x is equals to 2x. So it's really easy for us to calculate. But of course, it's easy because the curve is really easy. That's like the easiest non-linear curve that you can have, okay? Now, the cool thing with computers is that they are really good at calculating derivative. And here I have 2 dimensions, but imagine if you have to calculate a derivative in n dimensions. That's really hard. For us, it's really hard, but for a computer, it's like piece of cake. It's just going to take me longer if I have more dimensions and if the curve is more complex. But I can do it, right? So why do we need that? Well, we are going to apply something called error reduction. So I told you that to calculate those W's and those B's, the computer is going to take known data, and then they are going to try some values of W's and B's until they get a good result which corresponds to the classification, to the labels that we gave them, because this is supervised learning, okay? So let's imagine, oh, and by the way, data scientists love to use terms that nobody else understands, so they don't talk about error reduction, they talk about loss reduction. Okay, it's a word. So let's imagine that we have a system with 2 inputs. It's an easy system. And then if we give some data to the computer, we are going to tell them, oh, if you take a known value of W1 and W2, you're going to have a big error. That's the yellow peak that we have. This is a big error. This is a big loss. You don't want to go there. But let's imagine that if you take another value of W1 and W2, for example, this one, oops, let's go back, then you have a very low error. So that's really where you want to go. And then, by the way, on the way, there are dangers. You see, there is a local minimum at some point. There is a hole, but the hole is not as deep. So you don't want to go there because you're going to get stuck in there, and this is not the best possible value, right? So that we can teach the computer to do. So how do they find the deepest possible way? Well, it's like when you walk up the hill to go to the church up there, right? You're like, okay, this is really steep. Maybe I'm going to take a path which is less steep, so we know that, okay? So basically, the computer is going to use derivative functions. So they are going to start in a random point. And then they are going to say, all right, I'm going to find out the slope in this direction. Okay, it's pretty steep, but it's not the steepest. The steepest is actually high there, right? So they are going to calculate multiple derivatives so that they find the steepest way. Then they are going to take a step in the other direction because we want to go low. Now, how long of a step are we going to take? Well, it depends a little bit about the system. If you have a system that you know well, where you're not expecting that on the way there will be suddenly a peak or there is a hole on the way, something which is rather smooth, then you can take a big step. And of course, it's going to go faster because you take a big step and then you have another point and you're going to start again to calculate the slope at this point and then to go down and to go down. If on the other hand, you don't know your system well, if, I don't know, there might be surprises on the way, maybe you want to take a small step and go carefully, which of course is going to take longer, okay? So now we are one step lower. So ideally, this step, the length of this step is called the rate of learning, by the way. Now this step is going to lead you, hopefully, if everything goes well, all the way to the global minimum there. This is where you have the lowest error, okay? But of course, sometimes, depending on the landscape that you have, you're going to maybe to end up in a local minimum. Now, this is pretty good, but it's not the best. So in order to reduce that, you're going to try again, but this time with another starting point. And then you're going to try again with another starting point, and you're going to do it many times. Now imagine what a computer needs to do to have that running, right? They need to take a random point. They need to calculate a derivative. Here I have 2 dimensions. This is easy, but imagine n dimension in your system. And then you have to calculate the derivative, and then you have to take a step, if possible, not too big, because you don't want to risk missing something. Then you're going to do it again and again. And then you have to repeat the whole thing because you want to avoid local minimums. That's why training AI models is taking a long time. All right? But nonetheless, at some point, we get some good results, and you can have really complex landscapes. This is an actual loss landscape that I found on the web for a neural network. You see that you have a lot of local minimums, so the risk of getting stuck is very high. That's why you need to try again and again and again until you find the deep part down there, here, right? Which is, all right, that's where we have the values of W and of B's, and we have many W's and B's, which give the best result based on what we taught the computer on the supervised materials that we gave. Trying again and again and again, this is called an epoch. All right, so you take a random, you do a descent, you get a number, then you try again, this is another epoch. We're going to try again, then you do another epoch. Like everything, there is an optimal number of epochs where if you do it more, it's not going to improve the result enough that it's worth it. So up to you to try with 5 epochs, 10 epochs, maybe you're going to go to 25, then you try 30, and then you notice, oh, the result is not better. It's not significantly better. So I'm going to use 25, okay? So in practice, this type of descent, we call it a gradient descent, where basically you take the gradient of a slope and then you descend. It's very expensive to compute, all right? They call it stochastic descent, which is essentially, it means random. So a stochastic descent means that instead of making sure that we are going down the steepest slope, we are going to try multiple directions in a random manner. Then we are going to see what sticks. It takes typically less long than to actually calculate the derivative of your function and then going down, all right? But it's also less precise. So up to you to see what you want to use. Stochastic just means random. So let's see an actual example. And here I want to really thank my colleague Seth, who actually knows what he's talking about. Now, I was in Italy recently. Actually, it was not that recent. It was before COVID. But and I showed an example like that. And I said, OK, so we are going to recognize if this is a pizza or a hot dog. And the Italians told me none of those is a pizza. OK, fair enough, I guess. But, you know, from an American standpoint, the top is a pizza and the bottom is a hot dog. So we're going to take those definitions. All right. We're going to use some tools in the short video that I'm going to show you. First of all, Python. Why is Python probably the most used language in AI? It's because of the tremendous amounts of libraries that you have. A lot of mathematicians and data scientists created libraries. Some of the thing is really in the language, right? For example, remember the dot product that I told you? Well, in Python, it's one operation and then you're done. Okay, well, if I did that in C#, for example, if I don't have a library, I need to do it manually, okay? So Python is very much used in AI and deep learning. Then we have PyTorch. So here we are going to use PyTorch. It's a framework, a library, if you want, which is going to have a lot of functions, like, for example, the gradient descent thing, you know, training the model, etc. This is all built in, and it's quite efficient. An alternative could be TensorFlow, for example. There are a number of frameworks like that. Now, Seth, in the video, is going to use Jupyter Notebooks. Notice the py in Jupyter. Okay, this is a Python tool. Py is Python. And essentially, it allows you to try things out in your web browser. This is super convenient because it allows you to try things in a fast manner. You can change the code a little bit and then run it and then see the result immediately, and then you change things a little bit again and then run it and then you see. Plus, Jupyter Notebooks also can connect to things like Azure, for example. Why do we want to connect to Azure? Well, because on Azure you have some really beefy GPUs that you can use to train your model faster than my poor Surface Pro 7 here. That one doesn't even have a GPU. I think it has a PU only. It's like, oh my God. So anyway, we want to pass that to big computers, and we are not going to actually buy those computers because it's too expensive. We are just going to rent them from Azure, okay, for a period of time. Visual Studio Code in the demo is used to edit the Python code. I'm just plugging it in here to say there is a Python extension in Visual Studio Code, which is really cool. It allows you to do things like, you know, the color coding and the auto-completion and things like that. So it's quite convenient. We are going to use Azure Machine Learning. Like I said before, we want to have some beefy computers with big GPUs and a lot of RAM and easy access to big data. So on Azure, we have all that with fast connections and very fast computers. This is called Azure Machine Learning. And then once we have our model, which is essentially a container, so it's an endpoint, it's a microservice if you want, which is going to tell me, hey, take an image and tell me if it's a pizza or a hot dog. We are going to deploy that to in that case, Azure Container Instance, which is probably the easiest way you can run a container on Azure. Obviously, you could use Docker, or you could use, you know, AKS if you like pain. Oh, sorry, I didn't say that. If you like to have full control over your system, I think that's the official party line. So AKS is great because it allows you to have resiliency, etc., etc. But here it's not necessary. So we're just going to use ACI, Azure Container Instances. So let's take a look at this video. All right. Oh, that's a great start. Let's take a look to the actual video. All right. So NDC and this demo. Here we go. All right. So I'm going to pause through the demo and explain to you what's going on. First of all, he's going to start Jupyter Notebooks on his machine. Okay. This opens in the web browser. And then he's going to open a notebook that in big part was actually lifted from this guy here. So essentially, this is where you learn that data scientists work exactly like developers. They go to their Stack Overflow. It's not Stack Overflow, but they go there, they copy, and then they adapt. Okay? So that's what Seth did here. So he took some code which was doing image classification, and then he modified it to fit his use case more exactly. So first of all, he imports a lot of libraries. He imports PyTorch, Matplotlib to do some plotting, etc., etc. And then after that, you can run those cells, okay, as you go. He's going to basically take some pictures that are labeled, and the label that he chose, he just puts them into folders. He has one pizza folder, one hot dog folder, and then he has images in there. So the computer is going to say, all right, I know that those images are pizzas. I know that those are hot dogs. And he has actually, somewhere it shows in the video, 883 images for the training. That's a lot of data, right? Because the data is, if you think in terms of pixels, it's a lot of pixels. In order to make things easier for the computer, he's going to actually crop those to a square, and then he's going to reduce the resolution of the picture because you don't need that amount of data to train your computer. So he's going to make things a little bit easier by normalizing those pictures. And then here there is a cool method which is called train model, and basically my work here is done, right? I have a method called train model. Essentially, he's going to say, all right, so go there, and you see there are a few words that we recognize, right? Here we have epoch, okay? So he's going to try a number of times. And essentially what he's going to do here, you see he has some phase. He has a training phase and a validation phase, and we'll understand later why validating your system is important. It's basically making sure that it's correct, that it gives good results. So he's going to go and he's going to train the model. Training the model is essentially amounting to telling the computers, find the W's and the B's by using your gradient descent. And first you do that on the training, and then later you try the validation to check if it's actually correct, okay? All right, then later, let's just go back a little bit. All right, you see here, he ran the thing, and then he gets a training loss of 0.69. That's not great, right? I mean, the loss should be as low as possible. The error should be as low as possible. And the ACC here, that's the accuracy. That actually, is it good or is it bad? Well, it's only at 0.71. That's not great either. You want to go to 100% 1, okay? So interestingly, for the training, we would say the results are not great, but for the validation, it's actually not too bad. And you see, it did that in 24 seconds. So it did that just one time, and then it got bad results in 24 seconds. So it's not too bad, but it's still pretty long, right? I mean, in 24 seconds, I can, build my whole web application and all the dependency libraries, right? So it's pretty long. Nonetheless, he ran that only once, okay? So let's visualize the model. So here it just drew, you see the training picture. There is even a tattoo here of a hot dog, which I'm not sure who would put a hot dog on there. No judgment, sorry. So basically he sees the training. So again, this is a Jupyter notebook, which allows me to try things out and to see if it works, and I can easily modify something and see if it works again. Then he's going to basically save the model in a standard format, which is called ONNX, O-N-N-X. There are different formats that you can use to save your models like that. Now you can run the same thing in Visual Studio Code. So essentially it's the same code than we saw, but in Visual Studio Code. Let's run that. Okay, it's training with one epoch. You see minus E equals 1, so minus E is the epoch. You see the training number and the validation number. Now this is what happens when the computer does the things. You see the loss. Right, so he's trying things and he says, oh, this loss is lower. It should be probably a good place to go. And then here we get 0.59 loss. Okay, it's a little bit lower. 0.73 accuracy. It's not great. The validation is better, again, for some reason. Maybe the pictures were just clearer or something. We don't know. And then they save that. And then they have here the model in the output, which is this ONNX thing. And there is a cool visualizer, which is called Netron, that you can open an ONNX model with, and then you can see how it looks like. And you see there are some words that we talked about before. There is a ReLU here. That's a rectified linear unit. That's the ramp thing that we saw before. And then these are basically all the layers of my system, okay, of my model. If I open one of those layers, you see, those are all the values of the B's here, of the bias. They are similar arrays for the W's. Okay, so this is a model. This model is not great because it had only one epoch to calculate things. It tried things only once, but it's going to do the work. Now let's go to Azure and let's run things more efficiently and more times. So here, first of all, where is the data? The data, we are going to put it in a blob storage on Azure. And the cool thing is that they can actually mount it, so you don't need to copy-paste things all the time. You just copy it to Azure, and then after that, it's going to be mounted. So this is an example of data. So here you see it says it's mounted as a drive, basically. And then after that, it's going to run the model, so that's pretty much the same. And then the model is going to be saved. So first of all, let's run those epochs. I am speeding things up quite a lot. You see the value here, that's the time, right? We're already at 2 minutes and 24 and nothing happened yet. We are just waiting. So these things take time. Then we get a cluster, we start running things, and they're going to try things for 25 epochs. You see the curves, the curve which says accuracy should tend to 1, and the curve that says loss should tend to 0. That would be ideal. And then when you get a result which you think is good enough, you can say, all right, I'm going to use that. Everything is saved on Azure, so it's quite convenient. This is, again, Azure Machine Learning, right? The output, this is a model. And then the next step, we are going to actually create a container image using that model and deploy that to Azure Container Instances, basically to expose it to the public endpoint. So this is what happens in this step. You see that everything is managed from Jupyter Notebooks. That's quite convenient, right? Especially for data scientists who know Jupyter Notebooks really well. And then now he's going to try things out. So let's go and select a random picture of a pizza. Let's assume that it's a pizza. This is the URL where the service is running. He passes the value, and then it says, okay, that's a pizza. Let's take a hot dog. That looks absolutely disgusting, but nonetheless, let's replace it. And then here we go. We have a picture of a hot dog. So it seems to work reasonably well. Now, obviously, this was a simple example with only 2 labels, pizza and hot dog. All right, imagine that you want to do a classification on much more food. That's going to take way more time. You need way more training images. You need to collect those images, etc., etc. But nonetheless, this is, in essence, how things work. All right, so let's talk about a few concepts in the 10 minutes we have left. First of all, there are a few risks that you need to avoid. One risk is called overfitting. Overfitting is essentially when you have, for example, a cluster of points, and then you try to run a good curve through those points. So if you try a line, there is a lot of error. Okay, it's not great. This is underfit. And then if you try this is pretty good. Kind of looks like the points. There is still some error, but it's pretty good. And this is a very simple curve. Now, computers are overachievers. They want to be perfect. So they are going to try to calculate a mathematical function which looks like that. The problem with that, there are 2 problems. First of all, it's going to take a long time to calculate this curve. You don't want that. Second of all, it's great for the training data. But if you have an actual value which is outside of that, then suddenly you have an error again. So you didn't reach the goal. You reached the goal for the training data, but not for your actual data. Okay? So we say this is overfit. You want to avoid your system being overfit. To avoid that, there are different strategies. One strategy is that every time you run your system, you're going to dumbify, I just invented this word, dumbify your computer by killing 50% of the neuron. And you kill them in a random manner, right? That's what happened on Friday nights, I'm told, when you, I don't know about those things. So anyway, you kill the neuron, and basically you make the computer a little bit less efficient, less perfect, and then you see the result like this, you have better result. Another way to do things is to use the validation data. Remember, we have kept 20 images in this example to validate our system. This data can be used to try the model and to see if we are overfit. And to do that, what we are going to do is plot things. We are going to say, all right, that's the error on the vertical line, that's the loss, all right? That's the number of iterations. So the number of epochs. If we do a training, of course, the computer is going to try to go as close to 0 as possible with the training data. But then you validate with the data that the computer didn't see before, and then maybe you're going to see something like that, where it's diverging, all right? So your system is perfect for the training data, but it's not good for the validation data. So you're probably going to stop the iterations here, because it's not worth going further. It's going to take more time, and it's going to be worse anyway, all right? Now, there are other problems with AI which are way worse than that. The first thing is misunderstanding the data. Collecting data in AI is a big issue. And unfortunately, we have only a few minutes here to talk about that, but I have a whole other hour talk. I'll give you the link to the YouTube video where I'm talking about that, about ethical issues with AI. Now, the first thing is the pneumonia thing. So the pneumonia mystery is, a few years ago, some doctors and AI scientists came together and said, hey, it would be cool if we take patient history, we feed that in a computer, we train a model, and then after that, we take another patient that the computer doesn't know, and we say, is he going to get pneumonia later or not, based on his symptoms and everything, and his history, their history. And that's cool, but the computer found something really weird. The computer said, oh, if that person has asthma, the risk that they get pneumonia is lower. Wow. That doesn't make sense to a human, because when you think as a human doctor, you say, if that person has asthma, they already have an affection of the respiratory system. The risk that they get pneumonia should be higher, not lower. So why did the computer find that? Well, the problem is the data is flawed. The thing is, when you have asthma, you pay attention to your body in a different way than if you don't. And maybe you find that if you have difficulty breathing, you go to the doctor much earlier because you know that maybe there is something wrong with my lungs, okay? Then the doctor does some tests and say, oh, this is an early stage of pneumonia, we are going to treat it, so you're not going to get pneumonia. So that's really what was happening. Now, the computer has no clue about those things. They totally misunderstood the data. The computer said, oh, if that person has asthma, they didn't get pneumonia, so that's great. If that person who was never treated for pneumonia has asthma, the risks of them having pneumonia is very low. Don't go to the doctor. That's really bad, right? So here you can fix it in the data by saying, oh, I'm going to exclude everybody who has asthma from the training data. But what else did you miss in the model? And eventually they ended up not using that model because it was too flawed. What I'm saying here is that it's really important to always question your model, question your data. AI is not, I'm going to let the computer run things and then take some vacation. You need to be there. You need, the role is shifting, sure, but the role is super important, okay? Another issue, which is probably even worse from an ethical and moral perspective, is things like racial bias or gender bias. And again, it comes all from the data, but also from the people who use the data to train the model. So in 2015, Google had a huge bug in their model where basically when you would see a person of color, they were classifying that person as apes. Oh my God, this is terrible, right? You don't want to do that, definitely. What happened here is most probably, and I don't want to judge here, you know, but probably the team was very white and very male. And they didn't even think of trying the model with picture of people of color. Maybe they didn't have friends who were people of colors, all right? They just didn't think about it. And then you end up with aberrations like that. This is really bad. If you want to solve these issues, you need to collect a lot of data. You need to validate your data. You need to make sure that the data is not biased, all right? There is a very well-known phenomenon which happens, which is that police goes in poor neighborhood a lot more than in rich neighborhood. This is a vicious circle because rich people see some things happening in poor neighborhoods, they call the police to go there. The police goes there. If there is more police, there is a feeling of insecurity. And then the police goes there even more and even more and even more. And this is how you get this kind of bias thing happening, right? So you need to validate your data, but you also need diverse teams. I can guarantee you if Google had, you know, black engineers on the team, that wouldn't have happened because they would have tried with their own friends and their own family. And then they would have said, hey, there is a problem with the data and we need to fix it before we go to production, all right? So this is super important. Again, I hate that I have only 3 minutes to talk about those things, but first of all, we have some seminars that you can do. So this is actually a group which is led by Microsoft with data scientists and everything. And they have some seminars and some webinars that you can take. If your firm is using AI, I cannot recommend you more to have everyone on the staff doing that. Even the cleaning lady. Why? Because if the cleaning lady knows about those things and sees some things happening in her app or in whatever she's doing, she might report it and say, hey, there is a problem here, we should, you know, so train everyone, right? This is important that everyone on your firm is aware of those things, and probably the CTO even more than anybody else, okay? As I said, I have a talk of an hour about that. This is the URL, and by the way, you'll get the slides in a second. So go and check it out. I think it's a good talk. I had some good feedback on this talk where I talk about all those issues, but except I have an hour and not just 3 minutes. All right, I want to mention cognitive services. If you are a developer and you want to get started with AI, this is a good place to get started because we have pre-trained models that you can use with SDKs and APIs. You can call it and then you can refine the training, but at least you don't have to do the whole training by yourself. All right, so this is a place where you can go and learn about it. Finally, some resources. A lot of what you saw was inspired from an MIT course, which is available to everyone for free. It's multiple hours of videos. It's a really good course. I cannot recommend you more to check it out. It defines a lot of those concepts, probably in a more precise manner than I did. Microsoft.com/learn, this is our learning platform. You will find some learning modules about AI and about how to train models, etc. So you can go there. Jupyter Notebooks and especially the Azure integration is documented, as well as the VS Code for Python. Going to switch to the next slide, but again, don't fret, you will get the slides. Everything you need essentially is there. It's gslb.ch/NDC Porto 22-1. Why -1? Because I have a talk tomorrow. I hope to see you there. That would be cool. Or this QR code. All right. You will get the slides. You will get the videos that I showed you, as well as additional resources. And finally, I hope it was useful for you. Thank you so much for coming today. It made me so happy to talk to a live audience again in person. This is great. My name is Laurent Bugnion. I work for Microsoft, and I hope you like this talk. Thank you so much for coming.